Hello, I'm Michael White. I'm going to be reading from the 6th grade science textbook today. We're on Chapter 1, Lesson 2, Scientific Thinking. My Planet Diary. Inventor Extraordinaire. What does it take to be an extraordinary inventor like Elwood Haynes? Born in 1857 in Portland, Indiana, Haynes was recognized at an early age for his determination and curiosity. As a student and as a scientist, he overcame obstacles and went on to distinguish himself with many technological firsts. He constructed our nation's first long-distance, high-pressure natural gas pipeline. He created stainless steel and other metal combinations. Haynes designed the first successful gasoline-powered car in America, the Pioneer, which is pictured here. What are the characteristics of scientific thinking? Have you ever taken apart a flashlight just to see how it works? Or thought about whether a magician really sawed a person in half? Or told a teacher the truth about why your homework was late? If so, you've demonstrated some of the key characteristics of scientific thinking. Scientific thinking involves characteristics such as curiosity, creativity, open-mindedness, skepticism, awareness of bias, honesty, and ethics. Curiosity and creativity. Curiosity is one of the main characteristics that leads to new scientific knowledge. Scientists want to learn more about the topics they study. Curiosity helps them to make observations and ask questions. In 1609, Galileo Galilei demonstrated his telescope, which would lead to many new astronomical observations. Although Galileo's curiosity inspired him to observe space, it was his creative thinking that allowed him to make improvements to the telescope. Creativity involves coming up with new sources and ways to help solve problems or produce new things. Open-mindedness and skepticism. Scientists need to be open-minded or capable of accepting new and different ideas. But open-mindedness should always be balanced by skepticism, which means having an attitude of doubt. Skepticism prevents scientists from accepting ideas that are presented without enough evidence or that may be untrue. Skeptics of scientific claims, for example, can help determine if something really exists. Practice using open-mindedness and skepticism in Figure 1. Awareness of bias. What scientists expect to find can influence or bias what they observe and how they interpret their observations. There are several key kinds of bias. Personal bias. If a person's likes and dislikes influence how he or she thinks about something, that is called personal bias. For instance, if you like the taste of milk, you might think everyone likes it too. Cultural bias. When the culture in which a person grows up affects the way that person thinks, this is called cultural bias. For example, a culture that regards milk as a food just for babies might overlook the nutritional benefits of drinking milk later in life. Experimental bias. A mistake in the design of an experiment that makes a certain result more likely is called experimental bias. For example, suppose you want to compare the health effects of drinking low-fat milk and regular milk. Your experiment consists of two groups of people. One group drinks low-fat milk for a month, and the other drinks regular milk for a month. If either group had been less healthy than the other group before the experiment, your results would be biased. Honesty and ethics. Good scientists always report their observations and results truthfully. Honesty is very important when a scientist's results go against previous ideas or predictions. For example, in 1912, a group of scientists in Britain announced that they found a fossil that was the missing link between humans and apes. The fossil had the skull of a man and the jaw of an orangutan. They called the fossil Piltdown Man, as shown in Figure 3. About 40 years later, careful testing determined that the fossil was a fake. Scientists also need a strong sense of ethics, which refers to the rules that enable people to know right from wrong. Scientists must consider all the effects their research may have on people and the environment. They make decisions only after considering the risks and benefits to living things and the environment. What is scientific reasoning? You use reasoning, or a logical way of thinking, when you solve problems. For example, you notice that water on a stove boils when the stove is turned on. Because the water doesn't boil when the stove is off, you might logically conclude that the heat causes water to boil. Scientific reasoning requires a logical way of thinking based on gathering and evaluating evidence. Objective and subjective. Scientific reasoning involves being objective, which means that you make decisions and draw conclusions based on available evidence. For example, a paleontologist named Jack Horner and his partner, Robert Michaela, discovered the nest of a dinosaur called Maiasaura. The nest contained fossilized eggs, newly hatched babies, young dinosaurs, and adults. Based on this evidence, Horner and Michaela concluded that Maiasaura took care of their young. In contrast, being subjective means that personal feelings affect how you make a decision or reach a conclusion. For example, suppose that a paleontologist thought that dinosaurs were bad parents. If she found a fossilized nest of eggs with no bones of parents nearby, she might ignore other evidence and conclude that dinosaurs did not care for their young. Deductive and inductive reasoning. There are two main types of scientific reasoning: deductive reasoning and inductive reasoning. Deductive reasoning is a way to explain things by starting with a general idea and then applying the idea to a specific observation. You can think about deductive reasoning as being a process. First, you state the general idea. Then you relate the general idea to the specific cause you are investigating. Finally, you reach a conclusion. For instance, you know that water freezes at 0 degrees Celsius. You see a frozen puddle of water. You know that water has frozen because it was at or below 0 degrees Celsius. Inductive reasoning can be considered the opposite of deductive reasoning. Inductive reasoning uses specific observations to make generalizations. Suppose you notice that every time a puddle freezes, the temperature outside is at below 0 degrees Celsius. You might conclude that water freezes at 0 degrees Celsius. Faulty reasoning. If you make a conclusion without gathering enough data, your reasoning might lead you to the wrong general idea. Incorrect reasoning such as this is called faulty reasoning. For example, suppose you saw a number of people walking their dogs and observed that every person who was walking a yellow retriever that day was a young girl. You might use inductive reasoning to say that only young girls own yellow retrievers. However, this conclusion would be wrong. Scientists must be careful not to use faulty reasoning because it can lead to faulty conclusions. How does scientific knowledge change? Our understanding of the natural world is always growing and changing. New technologies expand the way scientists gather and interpret data. This increases and changes scientific knowledge. Today, scientists know about topics ranging from matter's smallest particles to the deepest regions of space. But this wasn't always the case. Scientific knowledge is based on an ever-growing collection of facts about the natural world, but it changes with new evidence or new interpretations. For example, 2,300 years ago, ancient astronomers thought that all the observable objects in the sky revolved around Earth. Later scientists proposed that Earth and other planets actually revolve around the Sun. However, there was no evidence of this until Galileo used his improved telescope and witnessed moons moving across Jupiter. Today, scientists know that Earth and all other planets in the solar system revolve around the Sun. And that is the end of Lesson 2.